Hello from AI Sciences, and welcome to Gradient Boosting Explained for Beginners Part 2. I'm your instructor Kashif Murtaza, and in Part 1 we basically discussed gradient boosting algorithm at a very abstract level. In this video, we are going to actually discuss the gradient boosting algorithm with squared loss. We actually will drive an example to get better understanding of how gradient boosting actually works. We will also discuss stochastic gradient boosting and the term overfitting with relationship with gradient boosting. So let's dive in and see how the gradient boosting algorithm works with squared loss. Let me first explain what do we mean by squared loss. So let's say we have the ground truth value yi, and we have some predicted value which is yi hat at ith example. The squared loss is actually, let me call that as squared loss, is actually just the difference between these two values and their square. That's the squared loss on ith example. Again, considering our training data as xi and yi, and considering this as regression data, I varies from 1 to n. That's a squared loss. There are some properties of this squared loss. For example, the gradient of the squared loss with respect to the prediction y hat is simply 2 times yi minus y hat. That's the prediction. That's the gradient with respect to y hat. In fact, the gradient has a negative sign because the derivative is taken with respect to y hat. And the negative gradient, which is actually the residual ri, the negative gradient, is basically minus the gradient, which is minus 2 yi minus y hat I, which turns out to be simply 2 times yi minus yi hat. So when we compute residuals or the gradients, when we compute the gradients, we actually come up with the residuals. And that's why these gradients are sometimes known as residuals. That's one property. The other property is when we compute the best learning rate, alpha, and if you remember from the last video, alpha can be found as something that minimize over all examples 1 to n. The loss function, in this case we are using squared loss, so squared loss function on yi, and the prediction yi hat plus the step in the gradient direction, negative gradient direction. So that's the, we want to find out alpha that minimizes this particular quantity. And if you see, this particular quantity is simply, if I just change the color, just to emphasize, this particular quantity is simply yi minus yi hat plus alpha ri hat whole squared. And to minimize this, obviously there is a sum outside, varies from 1 to n. If I want to minimize this quantity with respect to alpha, I will differentiate this quantity with respect to alpha and put the result equals to 0. And that brings basically 2 times the derivative actually is 2 times I equals, so it's 1 to n, and that is yi minus yi hat minus alpha ri hat. And then we have here negative ri hat. And if we plug in that equals to 0, we end up being the value of alpha can be found very easily. The value of alpha here is just, if you see, that is actually the sum of yi minus yi hat. That sum is equal to alpha times, this 2 goes away, this goes away, that is equal to alpha times the sum of all the residuals. And if you can see on the left hand side here, this sum is actually exactly the sum of all the residuals, but just half of it, because all the residuals, these are double like this. If I sum all the residuals, that is double this value. So the optimal value for alpha in the case of least square error is 1/2. So every time the best alpha can be found as 1/2. Now we know that the residuals can be found with this formula, and the alpha can be found just in least square. The alpha can be found just as 1/2. Now we are ready to write our algorithm using this squared loss, and you will see the algorithm is completely very simple. Let me write. So let's say the given data x1, x2, x3 ... xn, and the corresponding values that are given y1, y2, y3 ... yn, these are given. So the very first prediction is that y1 hat is equal to y mean, which is the average value. y2 hat is that is at time 0. That is at time 0. Yeah, so that's the time 0. That is again y hat. So I predict everything using the mean value. So yn at time 0 hat, my prediction is just the mean value. Then for t is equal to 1 to capital T, whatever my number of iterations are, what I really do is I compute for I equals to 1 to n, all my data points. I compute basically the residual RIT, and this is just, as you can see here, this is just this particular thing, 2 times yi minus yi hat. So that is 2 times yi, which is given here as a training data, minus yi hat at time t minus 1, which I already have computed here. So these are my residuals. The value of alpha is always 1/2 in the case of least square error, least square loss. And now I'm ready to get my new predictions y I at time t, which is equal to yi at time t minus 1 prediction plus alpha times ri at time t. These are my new predictions. So once this loop ends, I have my new predictions, and those new predictions are then go back to this, and the loop goes on and on and on. And after these t iterations are over, I will be having predictions that are much better than the predictions I started with. And that's all. This is the algorithm for gradient boosting. If you use the squared loss, it is this simple. I mean, if you want to code that in Python, it may hardly take maybe 5 to 10 minutes to just write a code for gradient boosting in Python, in plain NumPy, if you want to code it from scratch. Now let me discuss what do we mean by stochastic gradient boosting. If you have seen here in the gradient boosting, what we do actually is we initialize our predictions y at time 0 as y mean for all the data points. I is equal to 1, 2, 3. We initialize that. And then what we do, we use all the data. As you can see here, we use all the data from 1 to n, all the data points, to actually compute the residuals and update the model. Stochastic gradient descent offers, just like stochastic gradient boosting offers a much similar paradigm like stochastic gradient descent. It says rather than using all the data, just use a sample of the data, random sample of the data. So what that means is Rather than going through this loop for all the data, just subsample a data for, let's say, let's set some subsample size k is equal to, let's say, n over 2 or something. That's the subsample size. And randomly select this subset from the data and execute the algorithm and update your predictions based on this random subset. So everything works, but what happens is, rather than working on the whole data set at once and updating like in a batch mode, you update basically on the base of random subsample that you have picked. And rest of the story is exactly same. And the benefits of this stochastic gradient boosting is much like the benefit of stochastic gradient descent as compared to the batch gradient descent. A lot of efficiency, parallel execution, and online kind of learning. I mean, there are so many benefits of this stochastic gradient boosting. And in practice, when the data set is very, very large, this actually stochastic gradient boosting offers much. By the way, here, I just missed a step here. I missed a step here. I should have mentioned a step right here. You have to build a model here for model here HT that actually models the gradients, and this is this hat value. Yeah, I missed that. So I just remember that because one benefit of stochastic gradient descent is that on a small amount of data, fitting this model, this particular model, maybe in terms of regression tree or artificial neural network or stuff like that, that is much faster than building that on the whole set of data. So if you have very large quantity of data, it is good to go with stochastic gradient descent rather than stochastic gradient boosting rather than gradient boosting. So now finally, let me discuss the concept of overfitting here. It turns out that this gradient boosting is really very robust to overfitting, but it really depends upon the number of iterations that you move. Like in gradient descent, if the number of iterations keeps on increasing, then you may tend to overfit. And then also, depending upon the model here for actually modeling the gradients, negative gradients, depending upon the flexibility of this particular model, that actually model the gradients, the overfitting can be there depending upon how many iterations you are moving on. So it is always good to split the data in training and test set, or sometimes called the validation set. And rather than fixing the number of iterations to a fixed number, it is good to keep on increasing the number of iterations to the time where the validation error stop decreasing. And there it may be good to actually stop the number of iterations, and the generalization or the gap between training and test will be much better. So this kind of regularization or this kind of overfitting avoidance technique is sometimes known as early stopping, and this is very popular in artificial neural networks as well. So that's a more detail about gradient boosting. If you like this video, please press the like button, subscribe our channel, and share this video with your friends. Hope to see you next time.